Welcome to Fundamentals of Logic. Topics that we will cover include vocabulary, propositions and statements, truth tables, the laws of logic including duality and substitution. The rules of inferences will be introduced as well, but a second video will cover the rules of inference and quantifiers. Our first topic, vocabulary, propositions and statements. Propositions are declarative sentences that can be evaluated as either true or false, but not both true and false at the same time. Propositions are denoted by lowercase alphabet. Examples are P, Q, R, and S. Some examples of propositions: I have the proposition P, I am elected mayor. I have the proposition Q, I clean the streets. An example of a statement that is not a proposition: Lord of the Rings is the greatest movie ever, because that's just a matter of opinion. It cannot be evaluated definitively as true or false. Once you have statements, you can create new statements from old ones. First, you can use negation or the not. I didn't have a good not symbol to type in, so I'll just draw one. Here we have not P. We can also make new statements by using connectives. Our first connective is the conjunction and. And here we have P and Q. Next we have disjunction, which is the or, P or Q. And implication or implies, P implies Q. P implies Q also has a couple of other interpretations. You can also interpret it as if P then Q. In our example where P is I am elected mayor and Q is I will clean the streets, if P then Q would be interpreted as if I am elected mayor, I will clean the streets. We can interpret the implies also as P is sufficient for Q. Using our mayor example, that would be being elected mayor is sufficient for me to clean the streets. Two more interpretations of the implication: P only if Q, or Q is necessary for P. In our example, that would be I will not be elected mayor without cleaning the streets. Last, we have the biconditional over here, which is if and only if. P if and only if Q, which means P implies Q and Q implies P. So we reviewed our vocabulary. Our next topic is truth tables. Truth tables are used to evaluate compound statements. First, we write all of our propositions. In this case, we're going to consider the proposition P and Q. And then we make a column of all possible values of P and Q. 0 meaning P, the proposition is false. 1 denotes a true proposition. So here we have P and Q both false. Here P is false, Q is true. P is true, Q is false. And then at the bottom we have both P and Q are true. And I like to order this these values as if counting in binary. So here we have 0, 1, 2, and 3. Okay, so when we then go and evaluate a compound statement such as P and Q, we write in our truth values. Now P and Q are true only when both P and Q are true. P or Q is true when either P or Q or both is true. The implication, so this one's a little more interesting. The implication, often we call anything in front of this implies sign, in this case P, the assumptions or the givens. Whatever follows the implication sign, in this case Q, will be our conclusion. And essentially what happens is if your assumptions are false, you can always come up with a true statement. And then if the assumption is true, then it's only true if Q is also true. And then otherwise, if P is true and Q is false, it's false. So to kind of illustrate intuitively why this is the case, I like to go back to the example of P is I am elected mayor, and Q, I clean the streets. So in that case, the proposition is, if I am elected mayor, I will clean the streets. So let's just say that is the promise that I make while I'm campaigning. If I am elected mayor, I will clean the streets. Then we'll go and see all these different variations of P and Q and see if I've made a true statement or not. So if I'm not elected mayor and I haven't cleaned the streets, well, you can't really say I've made a false statement because I only said I would clean the streets, or the promise was if I were elected mayor, I'd clean the streets. So if I'm not elected mayor, I'm not obligated to clean the streets. So here again, when I'm not elected mayor, I'm not obligated to clean the streets. But if I am elected mayor and I don't clean the streets, then you would say that I have made a false campaign promise. And if I'm elected mayor and I do clean the streets, then you can say my campaign promise was good. So next we have P if and only if Q, which is the same thing as P implies Q and Q implies P. So you can break this up. You can do the truth table for P implies Q, you can do the truth table for Q implies P, and then add them together. But what you will see is essentially it's true when they have the same truth values. So when they're both 0 or when they're both 1, that's when it's true. Now we'll take a look at P and Q implies Q. So if you recall for the implication, as long as these assumptions are false, we're going to get a true statement. So let's look at P and Q and see where it's false. Well, it's false in all three, the first three values. And at the very bottom where it's true, we have to look at the value of Q. It's also true. So in this case, this is a tautology, meaning this compound statement is always true. Not P is essentially the inverse of P. So when P is false, not P is true. And when P is true, not P is false. Our last compound statement is not P or Q. So here, since not P is true, our or statement will be true because at least one thing is true. For our third line, here not P is false and Q is false, so neither is true, so the whole statement is false. And then at the very end, we have not Q true, which is enough to make the compound statement true. So the second thing to notice, no, not that one, are these two evaluations are logically equivalent. And they're logically equivalent, or we say that because they have the same truth table evaluations for all possible values of P and Q. A few comments on some of these features. First, a comment on this implication here, on why it is that when you start with a false assumption, you can come up with a true conclusion. So here, when P is false, the implication is always true. So we touched on that with the example of if I'm elected mayor, I will clean the streets. But on a bigger scale, what this is saying is that if you have false conclusions, basically you can come up with a true implication with any conclusion that you care to make. So in other words, bad assumptions with bad assumptions, you can basically prove anything you want. And that could be seen more obviously in that you could always just assume what you want to prove. Or another illustration of that is this math joke. So I'll tell you a joke now. So there are these, there's a mathematician, a chemist, and a physicist stranded on an island with a can of beans, and they're trying to figure out how to open it. So the physicist is trying to think of some sort of leverage and some sort of equations in order to get the can of beans open, and he's struggling with that. The chemist is trying to come up with some heat equations and somehow trying to explode the can open without exploding the beans everywhere, but he's kind of having some difficulty with that. And the mathematician is thinking, and finally he says, I've got it. He says, assume a can opener. So there you go. If you can assume anything you want, basically you can come up with whatever conclusion you want. The next comment I have on that, again with implications, is on this tautology. So the tautology is a pretty strong statement. It does kind of get to be trivial when P and Q are false, because then you, as we just discussed, then the implication itself is always true. But in this case, it's saying that no matter what P and Q are, if P and Q implies Q, then you're always going to get a true statement. It really doesn't matter what P and Q are. So it's a very strong statement about this combination, this compound statement, that it's always true. Lastly, a word about logically equivalent. And we'll see this later when we get to laws of logic, many examples of this, is that what this says is wherever you see P implies Q, you can always substitute not P or Q, and you will come up with the same truth table evaluation. So basically, their evaluations are always the same when they're logically equivalent. Oh, and one more comment back to the tautology. We'll see many examples of those when we do rules of inference. Now that we've covered vocabulary and truth tables, our next topic are laws of logic. The laws of logic are used to simplify logical expressions. They are very much like the laws of algebra, which are used to simplify algebraic expressions. In class, I will give you this handout, which includes the laws of logic. And this is a handout you're welcome to bring and use on your exams. But let me just blow up the laws of logic for now so we can talk about them. So the laws of logic are basically sets of logical equivalences. So the first one, for example, here we have the law of double negation, where we say not P is logically equivalent to P. So anywhere you see not P in a statement, you can just substitute P for it. The second law of logic, the De Morgan's laws, I like to think of those as sort of the way you distribute a negative sign across parentheses. The thing that you need to remember is your not P, and then it'll flip your or signs to ands, and it'll flip your and signs to ors. So the not, parentheses P or Q becomes not P and not Q. And here's the equivalent, or the corresponding De Morgan's law. We have the commutative law, which is a lot like the algebraic commutative law. We have the associative laws. We have the distributive laws, the idempotent laws, identity laws, inverse laws, domination laws, and absorption laws. And then I also added at the bottom of your handout the logical equivalence we did on that truth table. Whenever you have an implication, P implies Q, you can substitute, basically you can get rid of the implication by substituting not P or Q. And one last note, you'll notice that there's this kind of bold double implication sign. So it's the if and only if, but in particular it's telling you that this is a logical equivalence. One last note I should mention, the F naught and the T naught. The F naught stands for false, and the T naught stands for true. So we'll do an example using the laws of logic, which is to negate and simplify the compound expression P and Q implies R. So I'll start by doing the negation. I'll write the P and Q implies R. And I'm also going to let you know, I'm going to justify each step on the right-hand column. And I'm going to ask that you do the same when you turn in work so that I can more easily follow what you're trying to do. Now, because most of, well, actually all, if you look, everything, the left-hand side of all of these laws of logic involve ands and ors. So since I want to use my laws of logic to simplify, the first thing I'm going to do is convert my implication here to ands and ors, and I'm going to use this handwritten equivalence here. So it tells me, this handwritten equivalence tells me I take the negation of my premise and I OR with my conclusion. So I'm going to take the negation of my premise, which is P and Q, and I'm going to OR it with my conclusion R. And I will say that is, I'm going to justify it with this step here. So now what I want to do is I look at this and I see, well, I have this negation outside these brackets. So I'm going to use De Morgan to put the, to kind of distribute the negation inside. So I'm going to have the not, P and Q. But remember, when we use De Morgan, our ors become ands, and our ands become ors. So here we've used De Morgan. And now we can use our law of double negation to simplify this statement. So I'm going to get P or Q or not R. And this, of course, is double negation. And so here I am done. And if I wanted to, I could do P and Q and not R. Either of these is fine to finish. So to finish out this video, we've done vocabulary proposition statements, we've done truth tables, we've talked about laws of logic. The next things to mention are duality and substitution. Duals. Let S be a statement. If S contains no logical connectives other than and or, then the dual of S, denoted S superscript D, is the statement obtained from S by replacing each occurrence of and or by or and, respectively, and each occurrence of true and false by false and true, respectively. So in other words, just replace every and by or and every or by and. Every true replace with false, and every false replace with true. And then you'll have the dual of the statement. So examples of duals, each of the laws of logic pairs are examples of duals. The principle of duality, let S and T be statements that contain no logical connectives other than and or. The principle of duality, let S and T be statements that contain no logical connectives other than and or. If S is logically equivalent to T, then the dual of S is logically equivalent to the dual of T. Rules of substitution. The first rule, suppose the compound statement capital P is a tautology. If lowercase p is a primitive statement that appears in our tautology, compound tautology statement P, and we replace each occurrence of the primitive P by the same statement primitive Q, then the resulting compound statement capital P1 is also a tautology. And we touched on this when we were doing the truth tables, and we said that the tautology was very strong. In other words, it didn't really matter what the P and Q's were, that once it was a tautology, it was always true. Second rule of substitution. Let capital P be a compound statement where lowercase p is an arbitrary statement that appears in the compound capital statement P. And let Q be a statement such that Q is logically equivalent to P. Suppose in our compound statement P, we replace one or more occurrences of P by Q, then this replacement yields the compound statement P1, and P1 is logically equivalent to P. And essentially, that's just what we were saying about using our laws of logic. we can replace one logically equivalent statement for another. Now that we have covered duality and substitution, our next topic will be the start of rules of inference. The rules of inference allow you to conclude new statements. This is quite different from the laws of logic, which simply allow you to simplify logical expressions. With rules of inference, you will be making new statements. The rules of inference are in the handout that will be given to you in class, also can be found in your textbook. The rules of inference are written both in this kind of tabular form, you see on the left, and they are also written as these logical implications you see in this middle column. If you were to do the truth table evaluations of these implications, you will find that all the rules of inferences are tautologies. On the far right, you'll see the name of the rules. So let's take a look at some of these rules of inference. And what you'll notice is if you think about what these rules of inference mean, they'll actually make sense. And that's because they're logical. They're actually logic. Anyway, so the first one, let's look at rule of detachment or modus ponens. It tells you that if you know P implies Q, so if you know if P then Q, and you also know that P is true, then you can conclude that Q is true. So the conclusion is Q. You can see our assumptions, P and P implies Q. The conclusion is Q. It's also worth mentioning trivially if P and or P implies Q are false, then the conclusion is always true. We'll continue with law of syllogism. Here, if we know P implies Q and we also know Q implies R, then we can conclude that P implies R. Essentially, P will imply Q, which then implies R. So Q is kind of the middle route, but you know that P will eventually imply R. Modus tollens. Here you know if P implies Q and you know Q has not happened or not Q, then you also know that P has not happened. Going back to our if I am elected mayor, I will clean the streets example, what this is saying is if I haven't cleaned the streets, you can conclude, because I'm a truthful person, that I must not have been elected mayor. The rule of conjunction is pretty straightforward. If you know P is true and Q is true, then you can conclude P and Q are true. And you can go through each of the other rules, and again, if you give it some thought, you will find that many of them will make logical sense to you. So an example of using the rules of inference, establish the validity or show a counterexample. If Rachel becomes a supervisor and works hard, she will get a raise. If she gets a raise, she will buy a new car. She has not purchased a new car. Therefore, either she is not a supervisor or she did not work hard. A quick note, to disprove something, all you need to do is show a counterexample. It is not sufficient to show an example in order to prove something. The first thing we should do is put together some statements and then rewrite what we are known, our givens, in terms of our propositions, and then write what we want to find in terms of our propositions. So I'm going to make my proposition P, Rachel is supervisor. My proposition Q, Rachel works hard. Proposition R, Rachel gets a raise. And proposition S, Rachel gets a new car. We are given if Rachel is a supervisor and Rachel works hard, then Rachel gets a raise. We are also given Rachel gets a raise implies Rachel will get a new car. And last, we are given Rachel did not get a new car. We want to verify not P or not Q. In other words, we want to verify either Rachel is not a supervisor or she did not work hard. So I'm going to work this as a two-column proof where on the left I will show you my work, and on the right for each step I am going to give you a justification. And this is how I would like you to do your work. So step 1, I'm going to rewrite my given, which is R implies S. That was my given. And as my justification is I'm going to tell you, well, I'm just rewriting my given and I'm giving it a step name. Step 2, I am going to write not S. Again, this is a given, so I'll let you know my step 2 is given. Step 3, I am going to conclude not R, and I'm going to use step 1 and step 2 and my rule of inference called modus tollens. So let's take a quick look at modus tollens, which is over here. And I'm going to rewrite it just so it's big enough to see. But basically it tells you if you have P implies Q. So you have an implication, but you also know that the conclusion of the implication is false, then the assumption must have been false. So again, looking at what we have in our proof, we have an implication where the conclusion is false, so we know the assumption must have been false. Step 4, we have P and Q implies R, and that is a given. And then step 5, I am going to say not P and Q. And this comes from lines 3 and line 4, and again from modus tollens. So take a quick look. I'm using step 3, which says not R. Since that's the conclusion of this implication, that must mean that the assumption was false. So then my last step, I am going to do not P or not Q, and this is De Morgan. Not a rule of inference, but from our laws of logic. So again, it's kind of like distributing the negative, but your ands must become or. So now I have verified what I wanted to prove. So we've covered vocabulary, proposition, and statements, truth tables, laws of logic, duality, substitution. We started the topic of rules of inference, and then in our next video, we will continue the topic of rules of inference as well as quantifiers. Thank you for listening, and I'll see you in class.